Okay, so I have had a few students turn in 2.06, and I'm seeing some regular issues with. I want to give kind of tutorial on what is expected in the assignment 2.06 in geometry. So let me bring up on the screen here and just show you what we're looking at. What is the assignment? What are we doing on 2.06? So I'm pulling up right here on the screen the geometry. So I need to look at 2.06 to see what's expected, right? So I go down here and at 2.06, here's the instruction. This will turn it in. When I go to activities, there's nothing there but the plus sign or whatever where you can submit a picture of your activity. But let's go to the instructions. Okay, we're only doing option one because this has a work collaborative option that we're not assigning you to work with another person. So module two activity, and we're just looking at option one here. So we're going to create triangles independently, okay, not collaboratively. So it gives us a little story. It talks about there's some bank robbers and they're breaking in, overwhelming people at these three banks, right? And they say this group always works in this same pattern. So they want us to come up with some other patterns that might work in that. So read that, but let me go down to what's expected here. So it says, and so we have to, and here's all our directions. We start with this triangle right here. I want to point out right up here at the top, it does have a click here for printable graph paper. I've already done that. I've printed out some graph papers and I've drawn my triangles there, but you can print out or you can make your own, or if you have graph paper, that's fine. But you can, there's some printable graph paper right there at the top of the page. So using their triangle, starting with that on your graph, here's our directions. First, we pick a transformation. All right, you've been asked by the police to find one of the three locations that the gang is likely to hit in the coming weeks. All right, so we are going to choose one of the following transformations to help locate the gang. Either translation, ASA, rotation, SAS. Okay, so you're going to pick what you want to do, a translation, a reflection, or a rotation. And then here's the detailed directions. All right, so if you chose, so identify and label the 3 points that are a transformation of the original triangle, and then follow these directions. So if you chose translation of your transformation, this was a translation, along with the distance formula to show that the two triangles are congruent. If you do a translation or a reflection or rotation, the triangle should stay the exact same shape. These are rigid transformations. Rigid transformations do not change the size or shape. So the translation, since we're doing it by SSS postulate, that means to side, side, side. That's saying that if we translate it, all three sides of the triangle stay exactly the same length. They stay exactly the same length. So to show that, we have to use the distance formula and calculate the side lengths of both triangles to show that they are still exactly the same, all three sides. All right, so you have to show your work pair of sides to get full credit for that. All right, if you chose reflection, reflection says with ASA, that's angle, side, angle. So use the coordinates of reflection to show the two triangles congruent by the ASA postulate. Use the distance formula for the side. Anytime you're showing a side, it's how both. So use the distance formula for the side. And then for the angle, you have to show the angles are congruent, that this angle on this side of that side you chose is the same in both triangles, and the angle on the other side of the side you chose is the same. So it says you can use your slope to do that, which may be a little trickier. Slope works a lot better with a rotation. Or your compass in straight edge. It says, remember when you learned how to copy an angle, we can just show that the angles are the same. And I will show you how we will do that with a compass here in just a moment here. Get my compass ready for that. And then in rotation, you have to use the coordinates. It's the SAS postulate. You can use the distance formula to show the sides. You're going to pick two pairs of sides, and then the angle in between. Side, angle, side. The order is important. Choose these two sides. You have to choose the angle that's in between those two sides. Just like up here, the two angles you choose, you have to choose the side that's in between those two angles for the distance formula for those two sides, and then again show the angle is congruent. The rotation, slope may be a better choice than the compass, but I'll show you both ways. So that's the detailed directions once you choose one of those. Here are the questions. All right, you got to provide an answer to the questions. For translation, describe the translation you performed, details and the coordinates to explain how the figure was transformed. For rotation, how many degrees did you rotate it? That you can choose. Which direction did it go? Be sure to use complete sentences. Reflection, what line of reflection did you choose? I can reflect over different lines. What did you reflect over? Anytime you reflection, where is that mirror? Where is that line? And how are you sure that each point was reflected across the line? How do you know it was the same? Be sure to use complete sentences in your answers. Okay, so there's a question. So what are you submitting? All right, you're going to use paper to make a copy of it, picture of it, whatever. When you're done, scan the picture. The 3 ordered pairs with labels of the congruent triangle you created using your transformation. You'll have your original triangle already with the coordinates there, so you have your new one that you created on top of that with your transformation. Be sure to indicate which transformation chosen. Any work to prove sides or angles, right? The distance formula for any sides that you're proving the same with clear labeling of which sides you're doing, and shown by use of a compass or the slope formula for the angles. And then the answer to this question, depending on which one of these questions you have to answer. So that's what you're doing. So let me switch from that and just show you. I kind of summarized it all on a page that I just have for myself, so I don't have to go to Buzz every time I pull that up. And so I just made us a little summary page that I refer to, which you can do the same thing if you want to just copy and paste it out of there. But the translation, reflection, rotation, using side, 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 angle, side, angle, side, angle, side. There's the things you go submit, and there's the questions. All right, so how did we do that? How do we manage to do that? Let me show you with some transformations that I did. Okay, so let me switch to that screen so I can show you that. All right, should be popping up there in just a moment. But what this first one I'm looking at is a translation, right? Translation. It just moved. It did not rotate. It did not reflect. It just moved. It was just translating. So I've already done the translation. There's the original, right? The original. And I'm just going to go ahead and label it A, B, and C because you have to have some kind of label and show that the new point became A prime. A becomes A prime. B becomes B prime. And you don't have to use these labels. I know some people are using the bank names that they have on there and just doing the abbreviation or just, you know, the first letters of the banks. And you can use those letters, whatever you want. You need some kind of label to use on your triangles. But I did a translation of XY becomes X minus 5 and Y plus 2. Like this 6 minus 3, be 6 minus 5 is 1. So my new one is 1. And the Y is 3. 3 plus 2 is 5. So my new point becomes 1, 5. It went from 6, 3 to 1, 5 using this translation. Using that translation. So I've got my new transformation. I have my coordinate pairs labeled as I said to do. And then I'm supposed to show, right, with the translation, this is a side, side, side. So I have to use the distance formula to show that these 3 sides did change in the transformation, right? It's still the exact same length. So if you don't remember the distance formula, right in there somewhere. Distance formula, distance equals the square root of, you take the 2 x's and subtract from each other and square it. Take the 2 y's, subtract from each other and square it. X1, Y1, remember those should be the same point. The X1, Y1, and then the X2, Y2. Make sure if you chose from these points this one first, then that should be the first Y, right? Keep the 1s in front and the 2s behind. Make sure you're subtracting in the same order. So let's look at that on one of these. Let's do the hypotenuse. All right, so A to C, so this is line AC is equal to the square root of X, I'm going to make this my x1. So 6 minus -2 minus -2 squared plus 3 minus -3 squared. Okay, so what is 6 minus -2? 6 minus -2 means add. When you subtract a negative, you add. So that is the square root. 6 minus -2 is 8 squared plus 3 minus -3, again, that's adding 3 plus 3, is a 6 squared. All right, so 8 squared is 64. 6 squared is 36. When you square something, you multiply by itself. 8 times 8, 6 times 6. So it's the square root of 100. And the square root of 100 is 10. 10 times 10 is 100. So that is how long AC is. This is 10. So now I need to calculate A prime C prime. All right, A prime C prime. And you may want to get more paper to do this because I got to do this for these two, and these two over here. I'm not going to do all of those right here on this recording because I don't want to take up much time. I want to show the other ones, but that's what you will need to do. So if I look at A prime C prime, the distance of that is going to be, I'm going to make this my x1. I can do it either directly as x1, but I'm going to just do this one. 1 minus a -7. 1 minus a -7, I'm just going to go say it's plus 7 because when you subtract a negative. 5 minus -1 plus 5 minus a negative, so it's 5 squared. That's not a good squared. All right, so the length equals, again, 1 plus 7 is 8, so we've got 8 squared plus 6 squared, which is what we had up here. So we're going to end up with the same thing. So that's squared over 100, and that is going to be 10. So I've shown with the distance formula that this is also 10. That one's 10, this one's 10. When it translated, it did not change. I have seen some of you marking sides, and once I've shown that, I know that this side is the same as that side, and I can mark it like that, right? And I've seen people mark that those sides are the same. Now, here's where you have to be a cautionary. I've also seen them go over and mark that these are the same. But here's the problem. If I use one mark on these and one mark on these, I'm also saying that this is the same length as this. And that's not true. I haven't done this measurement yet, but I can tell that's not the same length as that one. These are the same. I would need to do 2 marks for those. And then when I check these, I might do 3 marks for those. So pairs that are the same, everything that's the same would have the same marking. So I wouldn't use 2 here, 2 here, 2 here, 2 here, because that's saying that all 6 of those are exactly the same length, and that's not true. So make sure that you're just marking things that are the same using the same notation. All right, that's important. We don't want to say that all 3 sides are the same length unless all 3 sides are the same length. Then we can do that. So I did the distance formula. I would have to do these. I would have to do it again for these because that was what I was needing to do for side, side, side. The last thing is the question. It says describe the transformation performed the original triangle. I started there right here. I did a translation of this. And then it says use details and coordinates to explain how the figure was transformed and use complete sentences. So I would write that 6,3 moved to 1,5 because when I subtracted 5 from the x and added 2 to the y, 6 minus 5 is 1, 3 plus 2 is 5, and the other points worked in the same fashion. Don't necessarily have to, it was out after the first one, say, yeah, the first one worked, and as long as it's true for the other ones, I can say I used the same process on the other 2 points and to get those. I would say by the distance formula, I showed that each pair of sides was the same length, and so this trend is true by side, 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 by SSS. This translation holds true by SSS or something along that line. You're showing that it's a good translation because all the sides end up the same. Because if they're not the same, something went wrong. You didn't translate it properly. So you're just having also look at reflection. For the reflection, I did this reflection over the y, right? So this is the y right here. So I reflected that over the y. And when you reflect something over a line, for the y, however far distance is, right? However far that is, this should be the exact same distance. Because when it reflects the same distance. However far you are from the mirror, you appear to be that same distance away from the mirror on the other side. That's how reflection works. A reflection would not be, unless it's a distorted mirror, with just a true reflection, should be the exact same distance. So make sure your points look like it's reflected. If I've got this point right here instead of right there, I'm like, well, that's really close, and this is a lot farther away, so something's wrong with my reflection. Right? It should be the same distance. Same thing, however far from my line of reflection is over here, it should be the same distance to its other point that is congruent to it. Its coordinated point should be the same the other direction. So since this is 6 units, because I went ahead and labeled my graph every other square just because I wanted to make it large enough. You can label your graph however you want, just be consistent. Your X and your Y needs to have a consistent scale. And I made mine, every other box is 1, and I did that on the Y's also. But you can do a different scale on X's and Y's, but it gets confusing if you just have small numbers. But a lot of times it's necessary if you have big numbers. So this is a distance of 6 using my scale, and this is a distance of 6 from the line of reflection. So it says what we have to prove for reflection is angle side angle. All right, so I would have to choose 2 angles and the side that's in between the 2 angles to prove that it is the same distance. So I'm going to say I will choose, let's say I want to do this angle and I want to do this angle and this side, because I have to choose the side that's in between the 2 angles. So I could do that with a compass, as I pointed out earlier. All right, so with a compass, to prove if I'm doing this angle, then this angle is the matching angle. It has to be the same. So the way you do that is I got to make my arc. All right, make my arc the same size without changing the size. I go over here and I'm going to make exactly the same arc. I think I'm moving my compass there. I'll get my other compass out and won't let me move it. All right. All right, so I'm going to make this arc. All right, I realized my problem. I don't have enough paper underneath it. It's going to slide. Need a good stack of paper underneath it. You have a single piece, it's going to tear and not hold true. So make my arc. You can see which arc that is. I need to erase these other arcs so I don't get confused in there. I'll make the same size arc over here. So once I've got my 2 arcs, then I'm going to measure the distance. How big is where I made that arc? How big is that? It's right there. That's the same. That's the mark there. So I need to go over here and show that this one, when I mark it, is the same. And it is. So when I showed my compass that this distance is right there, over here it's the same thing. So by the compass, I've proven that this angle, I'm going to mark it with red, this angle is the same as that angle. All right, that makes sense? So we need to do the same thing with this angle down here. Excuse me. And so I'll take my compass and I will make an arc again. And I'll go over here and make the same size. And then measure the distance. Pardon me. So the distance is right there. So I should be able to go over here and it should be exactly the same. And it is. So that's how with the compass I can mark. So now this angle, let's see, I'll do 2 marks this time. So these 2 and these 2 are the same. And then I would do the distance formula for this. All right, so doing the distance formula, I would say, oh, I did not label my points. A, B, C. So A, this is A prime over here. Reflected over, this is B prime up here. And C prime moved over there. All right, so checking that out. So if I'm looking at the distance of this, A prime to B prime. So A prime, B prime equals the square root of, what's one, this is x2 down here, -6 minus -6. All right, so -6 minus a negative, again, is adding 6 squared plus 3 minus -3. Minus the negatives plus, so 3 plus squared. So -6 plus 6, well, that's 0. That's 0, so that goes away. 0 plus 3 plus 3 is 6, 6 squared. So we just have 6 squared because the other one was a 0. 6 squared is 36. So square root of 36, which is just 6. So this is a distance of 6. So we would need to do that over here and same calculations. And when we show that's 6, then we can mark these the same. And if you want to, since we used one hash there, we can say 3, however we want to. Angle, side, angle, these are the same triangle, just reflected. All right, and then it says a reflection. What line of reflection did you choose for your transformation? I did a reflection of the y-axis. And how are you sure each point was reflected across the line? And then we can talk about the distance from the line of reflection, and that by angle, side, angle, they're the same triangle. Since they're the same distance from the line of reflection and the angles and sides are the same length, that this is a rigid transformation. So last one I want to show you real quick is, and again, you're just choosing one of these. You're not doing all three, you're doing a rotation. And the only thing different in the rotation I want to talk about, did the rotation counterclockwise around the origin. Because this is the point that it rotated around. It rotated around there and went up here, right? So that's the rotation it did. I could have rotated it around this point here, and then it would move down over here. But I didn't. I used this as my point of rotation in the origin. So I said that. Then 90 degrees counterclockwise. Counterclockwise went this way instead of going clockwise. So it says rotation uses side angles. Right, so side, angle, side. So let's say I chose to do this side and this side. That means I have to choose the angle that's in between them. Side, angle, side. I can't choose one of these angles because I got to choose the one that's in between there. Side, angle, side. Okay, so I would need to go over once it's rotated, and that's the same as this one and this one. That angle. So again, I can do the distance formula, which you would need to do on the corresponding sides. This is the same side as that one. Those correspond to each other, so you need to prove those are the same. And then you would need to prove that these are the same length. And once you do that, then you'd mark those. It'd say, yep, that's the same, that's the same. These are the same, these are the same. But then we need to show this angle. And I was saying with rotations, you can do, if we rotated 90 degrees, that means this should be a 90-degree angle because it rotated 90 degrees, which means it's perpendicular. It means the slopes should be perpendicular. Now that didn't happen to reflection. Those are not a 90-degree angle in the reflection. Let me show you that. This is not a 90-degree angle because it did not go 90 degrees. It went differently. That's not going to work. You don't want that to use that with the slopes. You want to use it with a rotation because if they're perpendicular, that means the slopes are going to be opposite reciprocals. Opposite reciprocals. I'll show you what that is if you're not sure. So 90 degrees. Let's look at, okay, the slope over here is undefined, right? Straight up and down is undefined slope. This is a slope of 0. Slope. This is a slope of 0. 0 and undefined are kind of opposite reciprocals because this is up and down has a change of 0 in the x. So 0 is in the denominator, and you can't divide by 0. That's why it's undefined. This has 0 in the numerator, and so it ends up as a 0 as a slope. So let's look at the slope of this line. Okay, so this line here. Let's go from here. Remember, slope is rise over run. Rise over run. So the rise over run, how much is this rise? We have this point. We need to find a place where it crosses a point. Crosses right there. All right. So between those 2 points, I could have continued all the way up to here if I want to. It should be the same. How much did it rise and how much did it run? It's a -3. It went 1, 1, 2, 3. Remember, every other box is a 1 for my graph. So rise over run, it rose 3. And then how far did it run? It goes from -2 to -1 to 0 to 1 to 2, 4. So the slope is 3/4. Again, if I wanted to just go from the end to end, it rose from -3 to +3, which means it went up 6. And it went from -2 to 6. Went 1, 2, 3, 4, 5, 6, 7, 8. So it'd be 6 over 8. 6 over 8 is the same fraction as 3 over 4 when you simplify it. So it's still a slope of 3/4. So this line has a slope of 3/4. What is the slope of the corresponding line over here? So let's start with this point. Where's the next point? Right here is where it crosses another point. This is kind of vague. It's in the middle. We'd have to guess. That's, what is that? -1.28 or something. So we want to make sure we get right on places where it does go through an actual point. So what is the rise over run? Okay, the rise is negative this time. It's going down. It starts at 6, it goes down to 2, which means it goes down 1, 2, 3, 4. So it went down 4, and then it went 1, 2, 3. So the slope is -4/3. Well, 3/4 and -4/3. 3/4 was the original slope. The opposite reciprocal. The reciprocal means you take the fraction and you turn it over. Right? We turn it over. Opposite means this is positive, so this is negative. Opposite reciprocal. If they're opposite reciprocal slopes, that means they meet at a 90-degree angle. That means they're perpendicular to each other. So this is 90 degrees. And so by doing that, we can prove that it was a 90-degree rotation because the slopes are opposite reciprocals of those 2 lines. So that proves that we've got angles in here because these angles are opposite reciprocals, being undefined and 0, and these are opposite reciprocals because they're 3/4 and -4/3. So this angle is the same as that angle. So by side, angle, side, again, you'd have to do those distance formulas. Side, angle, side, you've proven that those 2 triangles are congruent by 90-degree rotation. So that is what we're looking for at 2.06. Yes, there's a bit of work in that, but again, it's worth more points than the regular. So it's asking a little more. It's kind of putting together everything that we've learned in the unit, kind of all into one place, because we talk about rotations, translations, all this other stuff. The distance formula is in there. It shows how to do that in the lessons. If you click on the little orange tabs and open up the extra information, it does have the distance in there. Let me know if you got other questions, and we will see you in class whenever you're in class next.